Okay, well, 5 o'clock. This is going to be our presentation on OT networking protocols and the security with them. So today we're going to be going over some protocols. We're going to be covering 6 of them. Kind of a lot, but we're going to do some demos mixed in with 3 of them. We have 3 demos. And we're also going to talk about sort of the security aspects with each one of them and how they work. But then coming up here, just right now, we're going to talk about sort of, we finally mostly finalized what we actually were thinking of when we mentioned projects at the beginning, so we're getting that moving. But first off,
so if you haven't already, please sign in, and if you're not already in the Discord, please join. Going into the projects, just a little announcement on it. So next week we're going to talk a little bit more about it, but basically our initial thought is we're going to have a Discord server for like any kinds of like OT home mapping, and as well as like the main project we're going to be working on, which is an electric grid. So our main plan is to work on like simulating the process and then integrating like physical components to that, and then working that into attacking it and like implementing security and all that kind of stuff. So hopefully this will like add to your resume and other kinds of things, as well as just learn more about like OT from the hands-on approach, because we've talked a lot. We've presented a lot of different things, but it's one thing to just hear about it. It's one thing to actually like apply your skills to it. And yeah, so that's kind of our initial plan. We'll talk a little bit more about it next time when we talk about like Frosty Goop and stuff like that.
yeah, so before we get into like actual OT networking protocols, there's some kind of quick things we got to cover in case you forgot or haven't gone it over in class. So networking basics, OSI model, not really that important. All you really need to know, 7 layers. So if we mention it randomly, you're not going to be totally lost if you don't know what's going on there. It's more of a theoretical outline versus the TCP/IP, which is sort of like an actual implementation. It's kind of used everywhere. TCP/IP stack, standard IT, 4 layers. But the important thing to kind of understand if you haven't learned about like your basic networking stuff is this concept of encapsulation, where one protocol will encapsulate another protocol. So generally it's the higher protocols are encapsulated by the lower level protocols, because we'll be going over sort of like the protocol stacks, should we call them, of some of the industrial operations. So the first one we're going to be covering is Modbus.
So Modbus is a protocol that was invented in the 70s. So it actually came out before Linux and before Windows. And it has a master-slave communication model, which I know sounds kind of wrong, but the reason it's like a master-slave model is because the master like sends out a command to his slaves, and if he like does a broadcast to all of those slaves, the slaves don't respond back, and they only respond when spoken directly to. There's different types of Modbus, and that's kind of the reason why it's still used today. So the main one we're going to be talking about is Modbus TCP and Modbus RTU, but there's also the UDP and ASCII versions of the protocol. So why is it even used? Well, it's because it's simple. There's no vendor lock-in, which is a big problem in OT. So it's an open standard. And it's also easily adaptable to different kinds of protocol suites and stacks. So it was one of the first like industrial protocols to utilize TCP, and it rose in popularity with the rise of PLCs, which will kind of get a little bit more of an understanding why when we start talking about into the weeds of what the protocol how it actually operates. So going more into the master-slave communication model, as I already said, the slave only responds when directed by the master, and it doesn't respond when a master broadcasts all of its slaves. And also the master can only broadcast. So the slaves will never like send data towards the master in any case. It's only when they're actually spoken to. So your masters in the context of Modbus are usually like your HMIs, your SCADAs, your control stations. Your slaves are your like servers that you communicate with. So like the PLCs, the RTUs, a lot of it is like working with the registers of the PLCs and whatnot. As well as a thing to know when I'm talking about this is polling. So that's like when the master is constantly requesting data from the slaves. So going into the actual frames that are being sent, like when the master is querying the slaves, is the slave address. So, yeah. So the slave address is the address of the slave that the master is going towards directly, and so it can mean like only one address if it's just the request towards that specific slave, or all of the slave addresses. The function code, so this is like a hex code that is used, that is, like for the specific function of the request by the master. So this could be like 0x01 for like reading coils, or like 0x06 for like writing to registers. And so the data, which I'm going to talk about in a little bit, is really whatever the master is trying to actually do with his request. So like it kind of goes hand in hand with the actual function code. An error check. So this is like a redundancy check for, there's different ones depending on the actual master slave, or the specific like communication model for Modbus. So like you might have a different one for Modbus TCP, you might have a different one for Modbus RTU. And so in that bottom right corner, you can see that there's like the ADU and PDU. So ADU is just the application data unit, and then the protocol data unit, I believe. And basically, the PDU is just like the more important part of like what the Modbus is actually doing, and then that ADU is like the entire frame. So how Modbus actually organizes data, it's kind of important to know this when you're thinking about like sending through these packets and whatnot. So discrete inputs, so these are just like your the status of on and off, your coils, which these are like the physically changing on and off. So like the actual like on and off of like a sensor and actuator. The input registers is like the temperature of a tank, really like whatever variables that are at play with the registers and whatnot. And then this is like the general oh wait, I guess I already the set point. Yeah, so this is like the temperature set point for the, like that's like the holding registers are. So going into the actual security, there is none. So it's all plain text. There is no authentication. I mean, it was designed in the 70s. And if you have these devices that use this protocol, just segment them. Like, just don't even like think about trying to do stuff with it, other than it being in the industrial kind of side of the house. So the major attacks that involves this protocol, well, we've already talked a lot about the Stuxnet throughout this interest group, but the way it was used specifically for Modbus is they injected malicious ladder logic into PLCs using this protocol in Destroyer. So this was like another campaign on Ukraine's electric utilities, but this is the 2016 one. I've talked a little bit about the 2015 one and like the whole Phantom House thing. But with the Destroyer one, it had like a Modbus module that crafted malicious Modbus requests that open circuit breakers and trip relays. Going into gray energy, this was like a recon by the Russians on Ukraine, and they used Modbus to find out about the actual devices in these industrial environments. So they would like send Modbus read requests and find out like what kind of ID these different like industrial control systems had, and really just finding out about different ICS components through using Modbus. And Frosty Goop, which we're not really going to go too deep into today, but basically it used Modbus TCP to directly like write values to components, and turned off the heating for over 600 apartment complexes in Ukraine. So going into an actual demo.
Yeah, so this is on a Mac. Had to install it on a Windows VM, because another thing about Modbus is a lot of these older protocols are kind of only work on Windows. So some of the newer ones we'll be talking about actually work on a lot of them. But what this here is, you want to explain it, I guess.
Yeah, so this is like the Modbus pull and then the Modbus slave. So the pull is like your where you're actually writing the values, and then the Modbus slave is where the actual server. So you can't really write values into that.
No, you write the values into this one because
Oh,
it's
you do?
flipped. Yeah.
Oh, my bad.
In this case, because of course they want to make the software confusing, even though it's called the slave, think of it as this is your PLC or whatever, or maybe your sensor. So the other thing about Modbus is you don't have like variable names for the registers. So it's literally just like register, I'm in 2 right now. I'm just going to write the value like 67 or whatever. And so we tried to slow down the polling thing, but the maximum the software goes is every second it'll do a poll. So that happened really quickly, but as you can see, the number got updated in this component here. And so it's our register 2 is 62 now, and if we were to change.
And this is the Modbus RTU protocol through a serial connection. And we did that through this application called VSPE, which we use to simulate an actual serial port, in this case COM10. Yeah.
Oh, whatever. Yeah, so that's a pretty basic Modbus RTU demo of just kind of like you literally just write the value, gets sent across, the polling agent's polling, however setting you set it, and then it'll just show up on the master. So the next protocol we're going to go into is called PROFINET. This, well, it's an open industrial Ethernet standard for automation. That's kind of like, it's been evolved from Profibus, which is basically a version-ish of Modbus, but PROFINET is meant to provide the fast deterministic data exchange between all your controllers and your field devices, but then also with, say, your SCADAs, your control elements. And so some of its core principles is that it leverages like an unmodified Ethernet, so it uses the Ethernet protocol, layer 2, but it adds a real-time channel. So instead of using like the TCP/IP stack, it'll use a separate channel to do some of like the faster, more time-critical tasks. So you have your non-real-time, which is your standard stuff. Say you're setting a config, something like that. This uses TCP/IP, so just your normal, what you'd find in your everyday IT environment. So that's kind of shown here at the right side of here, where it's the Ethernet up to IP, up to the TCP, UDP, depending on what they want to use, and then kind of through here over to the PROFINET. And this, yeah, for your configurations and also diagnostics. Additionally, one benefit of using PROFINET is the fact that this traffic is actually routable, like outside of just the OT space, because it's using standard network protocols. And then we have this other one called real-time, and so this bypasses the TCP/IP stack completely. It does this by setting inside of an Ethernet frame. There's a field called ether type. This basically tells the Ethernet protocol where to send the data. Normally it's set to aux 0800 for IP, but for PROFINET they just set it to this 0x8892 value. Why? I don't know. I don't know if they just picked a random number, if it has meaning, but they just picked it. And so this is a software-based solution. So all you need is just to have switches that match the ability to be managed switches, so they can't just be unmanaged switches. And they'll route it directly via PROFINET, skipping this TCP/IP stack, giving you a lot faster cycle times, so down to about 250. Oh God, is that microseconds? I think it's microseconds. I'm forgetting my physics symbols. Then for like really time-critical tasks, so real-time was used for most operations inside of industrial complexes, dealing with like a sensor to a PLC output. But for asynchronous real-time stuff, this is a hardware-based solution, so this you need actual physical hardware in order to implement this part of the protocol. And this is for really high-performance motion control. So again, think it's like a car factory, and you have these arms that are welding a whole bunch of stuff on or attaching a whole bunch of parts as moving around, and you have cameras doing making sure the arms are in the right places. And so you need a really, really fast protocol to have your feedback loops be really, really quick, and so you use this asynchronous real-time. And so one thing that it does that makes it really, really fast, it uses kind of a scheduled time division approach. So it has 2 phases. First, it has the red phase. This is reserved bandwidth where only IRT traffic can be traveling. They also kind of schedule amongst themselves when they're getting sent across the wire. And then you have this green phase, which is for standard communication, which means any other protocol can go across the wire. So this means that you can have this asynchronous real time with having your standard, your configs come down using the non-real time protocol underneath PROFINET, allowing it to be kind of used with a lot of other protocols as well. So when defining PROFINET, you kind of have these things called IO controllers. Just think PLCs, IO devices. These are sensors or actuators. Then you got the supervisors. These are the SCADA systems. So that's important for knowing how to config PROFINET, because in PROFINET, you have to define your entire network and all the things that are inside of it. So GSDM file is what it is. It's a general station description markup language file. It's an XML. A lot of these are going to be in XML. The protocol, like network definitions, are going to be in XML at least. And so it kind of will define your device identity, all the devices on your network. Also, it has a modular structure. So say you have a PLC that's working and you configure it for your PROFINET network, and then it breaks, and you need to plug in like a different vendor or something. The vendor will provide you with one of those DML files, and it'll plug right back into your network, and everything will still function as if it was the same PLC underneath, even though it's not. So yeah, it's plug and play and multi-vendor interoperability. I hate that word sometimes. But as far as security-wise goes, non-real time, kind of it's just standard stuff, because it's literally just using your standard TCP/IP stack, everything like that. So you can set up firewalls, and it's secured with TCP. You also have the real-time and IRT. The issue with that is because they skip IP, a lot of like your firewalls are not actually going to work with it. So you have to do VLAN segmentation, and the security really comes from actually segmenting your network and doing good, secure network architecture, and not from the protocol itself. As far as attacks that have happened against PROFINET, the only one that I could find was an instance of there was a denial of service vulnerability that somebody found in some Siemens PLCs in a specific version of this file, and it's not too prevalent as far as the security space goes, only because a lot of the actors are nation state, and PROFINET is mostly found in manufacturing facilities, so not necessarily the most prime target. And then yeah, we have this table over here, which just kind of shows some of the different protocol things that like non-real-time uses. So it can be over TCP, UDP, IPv4, Ethernet, and kind of describe some of the stuff over there.
Okay, so going to DNP3, so this is the Distributed Network Protocol version 3, and basically this is another open standard communications protocol, mainly used for SCADA or remote monitoring systems. So think of like the communication between your RTUs, your remote terminal units, and your MTUs, your master terminal units, which are connected like the SCADAs. And it's meant for like time synchronization, and it's all event-oriented communication. And the main core principle is that the devices report when something changes. So with Modbus, your slaves can't actually like send data back to the masters. And DNP3, the whole kind of point of it is to have like your sensors and your things like your IEDs sends data back to your like master stations, which in the case of the DNP3 protocol, it's mainly used in electric utilities. So a lot of times you want to have, like if one of your power stations is going out, you want to have an event-oriented communication protocol where they can send data back to the master and let you know about it before it gets bad. And that kind of leads us into the next part, which is the master outstation topology. So the way it works is that you have your master station, which is responsible for initiating the communication by sending out requests, and the outstations, which collect data from the equipment and then store it in their local data store, and then execute commands based off of what the master requests of the outstation. So think of like a master station as your SCADA control center or like your DCS or whatever, and then your outstations being more like your RTUs. Going into like class-based polling, this is basically like you configure different classes based on priority, whereas like class 0, it's a special class where you have like all of your Statica data. So this works well for like later when I talk about integrity polling. But this whole class-based polling really matters for like your outstation's ability to detect changes in its data points and classify them as events and work with the master station. And so like for classes 1 through 3, usually prioritize the different classes based off of like what their how high of a priority they are for your environment. So like class 1 has the highest priority and like class 3 is the lowest. And in some cases you'll have like your master poll like class 1 every 5 seconds versus like class 2 for like every 30 seconds and then class 3 for like every minute or whatnot. So yeah, and integrity polling, so this is kind of, you only do this in specific scenarios, so like on the initial connection of an outstation and a master station, where it will like basically make sure that like populate the master's database with a complete snapshot of the outstation state, or like after restart, or periodically. So it really just, the integrity polling is just to make sure that everything is okay on the outstation point of view. And so security, there is a built-in security protocol for DMP3 called DMP3-SA, but no one actually uses it. There's this YouTuber who has like 30 plus years of experience in like industrial control systems, and they pretty much just say, yeah, no one uses it. We like the insecure version better. And the original one is just kind of like Modbus. Security-wise, it's all in plain text. There is no authentication, and it's susceptible to pretty much any cyber attack that an insecure protocol is susceptible to, like eavesdropping, man-in-the-middle, denial of service, replay attacks, etc. When it comes to actual attacks, there isn't like anyone that like specifically notes DMP3 in like these malware reports, so it's kind of hard to know which ones actually been used in, but it is widely used in critical infrastructure, especially electric grids.
Yeah, speaking of electric grids, we have this amazing protocol name, IEC 61850. Why they didn't give it a name, I don't know, but that's just the definition of the standard, IEC 61850, that they've made a protocol off of. So this is, it's an international standard for communicating networks, specifically in power utility automation. So this can get linked heavily with the DNP3, but the primary goal of this is to standardize all of the random proprietary protocols that kind of existed before this kind of came out inside of the power grid space, and also to replace a lot of like hardwire connections. And when we're talking about like the power grid space, hardwire connection isn't like an Ethernet cable. It's literally like a copper cable that's carrying current. And also, yeah, to replace those proprietary protocols. Because when I was researching this protocol, there were a lot that it replaced. So I'm kind of glad it exists now. So as far as the system architecture with this one goes, you have your station level, and this is kind of like, this is your SCADA HMIs. It's used for like substation control and monitoring. And then you also have your bay level. Now this is like your PLCs, and then specifically inside of these power plants and stuff like that, they use a lot of IEDs, which we talked about kind of briefly in the last meeting about components. But when we're talking specifically about power stations, IEDs are like one of the biggest components of it, because while they don't like totally do what PLCs do, because they control power inside of a power grid, you're starting to, it's like, okay, well, that's sort of what you need. So they're used a whole lot in here. So it's mainly IEDs. That's why you can see in this image here, it's saying it's just IEDs here, even though there are still PLCs and stuff like that at that level. And then finally, the process level. This is, you got your switch gears, your circuit breakers, switches, you know, your transformers for current and voltage as well. Now, IEC 61850 kind of has a service for every need. So you have your manufacturing method specification, or MMS. This is sort of just like PROFINET had like the non-real-time, which kind of uses standard stuff. This is the IEC's version. So it's a client-server protocol that runs over TCP/IP. It's used for the non-time critical communications like SCADA requests, configuration, and reporting. And then we have this one called GOOS, or Generic Object-Oriented Substation Event, which it's very, very high speeds, and it's also peer-to-peer. So this isn't like a system that will go from like your sensors up to your like SCADAs. This is one that's like a peer-to-peer, so sensor to actuator, or sensor to sensor, or IED to IED. And this is also for critical events like trip signals. So a lot of this in your power stuff has a lot of trip stuff for safety, so you don't fry your equipment and stuff like that. And so this one, again, bypasses the TCP/IP stack to operate directly on layer 2, kind of similar to how PROFINET did by setting that ether type field. And then this one can achieve delivery times under 4 milliseconds. And then we have this third one, which is SMV, sampled measure values, but it's also just called sampled values. Kind of depends where you look. They're the same thing. And so this is serialized data. And what this is used for is, well, it was mainly put in place to replace the thousands of copper wires. It also operates at layer 2. This is for data that's getting sent from your sensors to your PLCs or IEDs, whereas your Goose is going to be sent at those IEDs between them and also between the sensors and actuators. And then MMS is really just that top level between your IEDs and SCADA. So one thing that it does that kind of like PROFINET and IEC and one we're going to cover at the end kind of does is this abstract data modeling. So this is going to be organized into hierarchical, object-oriented models. So it kind of makes sense if you take any computer like programming classes here when you go over object-oriented stuff. And it's divvied up into logical nodes and data objects, which like aren't that important except for understanding that they exist when you're trying to find what's in your network, because again, just like with PROFINET, you had to define in this massive file all of the stuff in your network. With the IEC protocol, you also have to do that just using its config stuff. So it has its own language, substation configuration language, or SCL for short. It's also an XML based language. We love XML, I guess. And it describes the entire substation, includes all the devices, all the data models, and also the communication links that they're using. And this kind of enables the vendor independence. So just like with PROFINET, that's one thing that's kind of really important for a lot of these industries, is making sure they don't get locked into a vendor, because that increases their expenses by just an insane amount. And then security-wise, there has been some stuff with the SCL file tampering. One of them is called Indestroyer, which was it's a ICS protocol toolkit that kind of went after a lot of these protocols with just reconnaissance and stuff. So that's kind of with the SCL file tampering. Then you also have the Goose and SV. There's no built-in security. Again, when you're dealing with like the time-sensitive data, there's literally not enough time to encrypt stuff. Like encrypting it would take about the same amount of time it would take to normally just send it across. So they're like, we're not going to double our transmit times. So let's just stick with no security is in their mindset, so we can actually operate. And then the MMS, sort of just like with the non-real-time and PROFINET, again, you got some standard TCP/IP, but you have, specifically in the IEC, you got some remote code execution with some like weird buffer overflow shenanigans. I did not fully understand it. It's kind of crazy. And then you also have denial of service, just kind of like with everything. And then, yeah.
So yeah, MQTT. This is the message queuing telemetry transport protocol, which is based on a publish-subscribe model. And what publishing and subscribe model really is you have topics where people will like you'll have sensors and whatnot that publish data to these topics, and then you'll have different components that subscribe to that same topic. And it's really nice for like IIoT data synchronization and whatnot. And it also consists of mainly clients and brokers. So you have that one broker that manages all these topics. So when you have like a PLC that's publishing sensor data to their topic, that it will publish that data to the broker, and then that broker will then send that data off to all the different people or the other different components that subscribe to that same topic. So going into more of how the actual protocol works, so you may have heard of quality of service with things like internet protocols and whatnot, but the quality of service for the MQTT protocol is much different because it's baked into the actual protocol. And what quality of service means in the MQTT protocol is the level of guarantee that the client broker is receiving the actual messages and whatnot. And so for quality of service 0, it's like if you throw a ball over a wall and there is no acknowledgement that that ball was received. So pretty much you're sending data, and then you don't really care if you get a response or anything like that. And level 1 is you throw the ball and you wait for it to be thrown back to you. And then you have quality of service 2, which is you ask the other side if they're actually ready, and then they respond back, they're ready, and then you're like, okay, I'm gonna actually throw it, and then you wait for an actual response. So a little bit different than all the other protocols because with this quality of service. So going into an actual demo of MQTT in action. So I got my broker, my publisher, and my subscriber. Okay, so I'm starting all the containers. So there's like 3 parts of this. I'm going to show each of the quality of service levels and the actual like packets being shown. It's kind of hard to show it in Wireshark, but there's this thing called POW MQTT, which makes it easy to actually show it.
Broker.
So going into the actual broker, so you can see that it opens up the socket. You're getting a CONAC, that's basically just a connection acknowledgement packet, and it shows like the subscriber is subscribing, and then it has like a subscription acknowledgement packet, and then it just shows the publishing of the data to that topic, and so that's like the quality of service level 1 or level 0. Oh my god. And then level 1, when we look at the broker, we're actually seeing with all this like publishing of data, we see a PUBAC, which is an acknowledgement of the actual publishing of data. And then if we go to a quality of service 2, we can see that there's the it's a little bit different. It doesn't have the publish acknowledgement. It just has like these like the publish, and then the pub rec, which is like the receiving, and then from like the client, the subscriber side, and then the pub release, which is from the the publisher side, and then the pub complete from the others. The subscriber side. So that's pretty much just like showing, you know, how the traffic looks like with a different quality of service, and how the packets, depending on the QoS you have when you're using MQTT, is much different. And we're gonna have a link to the GitHub be sent in the Discord general for this channel. That has like all of the code for the actual demo we have, and yeah, you go back to that.
Oh, yes, back to this.
And so going a little bit further into MQTT, so I've kind of just talked about how you have this broker, and a lot of cases you want to have like a cloud broker. So like you might have just this broker sitting in the cloud that's just getting straight up data from, you know, your industrial network, which is not a good thing. So to make it like, so you're not just sending all of your industrial data to this broker, there's this thing called bridge client, which allows you to have like, you'll have like a local broker and then a cloud broker. So the bridge client kind of acts as like a relay to connect the different MQTT brokers that may appear on like a network, and enable like that bidirectional communication between the local broker and the cloud broker. And so it will like subscribe to the topics on one broker, receive those messages, and then publish them to another broker like your cloud broker, and vice versa. So yeah, so going into a actual,
Where's
no, I'm
just hit L. No. Okay.
Okay, so as you can see from this diagram, like we have our first topic. I didn't label like topic 1, but so you have like your PLC 1, which is publishing data to the topic 1, and your HMI is subscribing to that topic. That topic, as you can see, isn't being subscribed to the bridge client because there's no one up here who's subscribing to topic 1, so it's only being processed in the local environment, so that data will never be sent out to the cloud. But when you have like your PLC, your two PLCs, topics 2 and 3, where they're publishing their data, since like you have these like the cloud dashboard and analytics that subscribe to a topic, which is a combination of topics 2 and 3, because with the bridge client you can have like the topics be meshed together, and so it's just like one topic that has like different parts of it. So that's another thing with bridge clients, is that you can filter out specific data. So like if I don't want to have like the status of my equipment being sent up to the cloud, because that would be a lot of extra load, I can just easily like filter and combine it into one topic being sent to the cloud.
Yeah, and so additionally with this MQTT bridge client, this is where you're going to config what you're sending up to your cloud broker. So your cloud broker doesn't get to decide what it's going to take, because otherwise that could be a security concern, right? You could just get into the cloud broker and be like, hey, send me all the data. But actually that's configured on the bridge client, so it's a bit more secure. So that's, So you're doing all your config for MQTT from your bridge client.
And the purpose of showing the historian DB here is to show that you can have a topic that isn't being like sent to the cloud or anything be subscribed to just like all the topics for that entire like industrial network, and just kind of get a combo of really anything. So yeah, going to the actual security for MQTT, there's a protocol which like a different version of the protocol called MQTTs, which is basically just MQTT layered with TLS encryption. So like when you have a connection over MQTTs, the connection must perform a TLS handshake before you can actually send your normal MQTT packets through that connection. So that's really about it when it comes to MQTT security. There hasn't been like anything I've seen with an actual like campaign or whatnot that has utilized it per se, like in the actual malware report, because in some cases we might not even know if it may have actually been used as a complete attack vector, but it is in a lot of these industrial environments, and it is bad if you have an MQTT server exposed to it or not.
Yeah. So now for our last protocol, and kind of most complicated, but only because OPC UA is not actually a protocol. It's a standard. So like PROFINET was a standard with kind of some protocols underneath it, but it still had its protocol. And then you had the IEC, 6A150, which is a standard, but it also had a bunch of protocols that were actually defined in it. OPC UA is a bit different because what it stands for is it's an open platform communications unified architecture. So it's a way that a whole lot of organizations can come together to create a secure and platform independent and also service-oriented architecture, network architecture that is. Now, this evolved from the classic OPC, which was horrible because it was insecure, had no data, and it used DCOM, which is a Microsoft's like application communication protocol, so like you could talk across different computers. So it was really bad. So literally, in order to use OPC, you had to have all your stuff Microsoft, and that's not really the case in a lot of these industrial environments. And so they came up and they're like, we should make this a great protocol. Now it's one of the most used protocols in industry. So the primary goal of it was to create a universal bridge for interoperability so that any company can come in with their stuff, write a couple things for the vendors, and then have it be able to be used inside of this OPC UA and network. It's also one of the only protocols that's like secure by design. It was made in 2006, but then they did like a massive revision in 2021, and it's kind of like making a resurgence in 2024 and 2025. So it's kind of one of the more newer ones. And so like the communication model that it kind of defines is that you should have, it can be client server or publish subscribe, because it can be running on TCP, it can be running on MQTT. It doesn't really matter because essentially what it does is it creates, it allows you to create digital twins. I'm jumping ahead of myself here. So it allows you to create digital twins. That's kind of what this image here is right here. You have your physical system. You have all your network data. This is very oversimplified because you're going to have a whole lot of OPC UA servers inside your network, but it sends to the OPC UA, and then it'll get sent out to your your virtual system, where you can do a bunch of tool analysis, data analysis in your IT cloud stuff. And then you also have it's, again, object-oriented as far as the data is concerned. And this protocol, along with security, also wanted to make sure that context is very important. So say you have your PLC and you're reading from its value and it's like 58. And then you send that value 58 up to your SCADA system, and it's a different engineer, and he's having to configure the SCADA, and he reads this value 58. And he's like, okay, where's this coming from again? It's just 58. Is this like time since a thing has occurred? Is it temperature? Is it whatever, right? So in OPC UA, they defined a way to actually share the data with a whole lot of context. So in addition to like labeling it, giving it an actual name, the data type, if it's a float, a Boolean, whatever. So yeah, that's essentially the communication model for that. And also, everything's a node inside of OPC UA when you're trying to configure these networks. Your devices are nodes, your variables are nodes, your methods or functions are nodes, and also the references. Like if you use a reference to another thing, say you write a PLC that is connected to another PLC that's like reading out a logical value. So inside of when you're making this network and the config stuff, you'd have to make sure that that reference actually saying PLC1 actually uses PLC2 would actually be a node inside of this reference structure. But okay, we're getting into actually how it works and the abstraction stuff. So a device, you have your device, communicates with an OPC UA wrapper or server. Now these can be built into the device, or they can be like separated from the device. And so you can see that right here. You got your PLC. It's communicating with an OPC UA server. Say this one's not built in. This one's built in, but it's showed separately. Then you also have the gateway server, which allows kind of like the access to the rest of the network. So this guy is the gateway server. This is the OPA UA server. And essentially what that does is it allows you to have your PLCs kind of have a separate thing that's kind of taken away from the PLC in order to provide the data from your PLCs or sensors or anything to be into a unified format that has security and has some like nicer features that you kind of would expect when dealing with data, and not just like this number 58 that's kind of around. Like with Modbus, you get the number 58, and you also get its like register number 932, and you're like, well, that doesn't tell me anything. With OPA, the reason why they did all this was to make it a better structure. So, starting at the lowest point, we have this. I guess I can turn on the laser. Okay. Oh, that's a pen. We don't want the pen. The pen is bad. So you have, in OPC UA, you have this use case specific protocol mappings. Now, what that means is essentially OPC UA is at layer 7 of the OSA model. So that bottom part is all the other protocols. So if you're running on Ethernet and then a TCP IP, that's just down here. You got to define what you're running on. Or if you're running on Ethernet and then MQTT, or any of those other things, you can also run this on top of PROFINET. You can probably run on top of the IEC protocol, but I don't think anyone actually does that. And then you have this, you can either be a client-server model or this publish-subscribe model that you can define inside of what you're doing. Specifically with each server, this doesn't have to be across the entire network, so it has a lot of configurability. And then you have this information model access. So this is kind of that stuff I was talking about, where you can actually browse data. So if you go to a server and you don't know anything about what's actually there, how it's being set up, there's a functionality, a function that's written into all of them that allows you to just kind of tell you, here's everything I have, so you can quickly kind of define what you need from it. And so then this also provides all the context for it. And then you have this information modeling building blocks. So this is kind of, again, I think it's an XML on top of all of this other config stuff that kind of defines more of this context. And then finally, you have core information modules. So this is, think of them as like functions or classes. So you have like your core stuff with this like analog data. If you want to have an alarm, there's like an alarm class basically that kind of does all this basic stuff for you. And then they have this companion information modules, which is kind of a step above the core. So they came together with a bunch of robotics companies who were like, hey, what would be a really good thing to just have like a package almost that'd be good for like all of your robotics needs. And so they do that with robotics, CNC machines, wind power, PNID exchange, all that type of stuff. And then on top of that, there's a lot of vendor extensions you can use. So if you do want to stick to one vendor, You can have like additional vendor extensions, or even if you want a vendor extension on one of your servers that's like, say you have like a bunch of Siemens PLCs, you can have specific Siemens extensions to your OPC UA server that are connected to those that are going to provide you with some extra stuff. So this is just, so OPC UA is defined by the OPC Foundation. We got to make that bigger.
The green's just hard to see.
Well, we don't need to read the green. The green's not important.
Yeah.
So this is the base file that's logged in when you load up any UPCA server. I think I said that back. What does it matter? And so one thing that it likes to do is it creates these aliases. So this alias is a Boolean is going to be this value I1. So you can say Boolean or a bunch of shortcuts to make things a lot easier for a bunch of their scripting stuff. Additionally, in industrial protocols, a lot of the older ones, because they have these register values, OPC UA wanted to kind of not like knee-jerk change all the people who are used to those protocols. So they added these aliases. So you can say Boolean or you can just say 1. So they have all these defined. And then we have these objects. And so this is what I was talking about with like the object-oriented programming. Not programming, but so this is an I3062 or a default binary. And so you can have a description name and stuff like that. And I mean, as you can see, this file is massive, but we'll post a link to this if you want to take a look. But this is the default implementation of an OPC UA server that defines all of the data types that you can have, all of like the exposing functions that you might need, all of that stuff. Now, did I have it? Nope. Python. Oh, we got to run the server first. Okay. So if we just look at this stuff here, this is an example of the server kind of broadcasting everybody, hey, here's everything I have set up. So it has like the dictionary keys of the current, a whole bunch of stuff. Client. Now, this is really fast. But if you can see, you have this no data change event, and you can see this value is kind of changing. Let's just, okay, scroll up here. So you can see that when this demo is of a publish subscribe model with a really quick subscribe time. So what's happening here is the server I'm simulating, I don't even remember what I'm simulating. I'm simulating something. And it's changing a data point and exposing this point. And then you have the client, which is subscribed to all of those data points. It's recurring them. And as you saw, it was going really fast back and forth, sort of like the MQTT, because again, OPC UA is sort of like a standard that kind of can build off of MQTT. Because MQTT is just a layer 4 protocol, just for the transport, and this is layer 7. Yeah. Let's go back. Wow. So this is a security by design, as I keep mentioning. So security is like a core, and it's also mandatory to the specification. It's not like an add-on like some of the others. Like with PROFINET, there's called a profile, which is like add security to it. But again, not many people use it. It also uses X509 certificates for the application and authentication. So this protocol actually uses a lot of the security. It provides message signing, integrity, and encryption for confidentiality. And it also supports user authentication and like fine-grained authorization. So you can give access to only specific devices on your OPC UA server. So you can figure it there or globally or all that stuff. As far as attacks go, the in-controller, it's a pipe dream toolkit. They built a specific toolkit to try and break OPC UA. It wasn't used like in the wild, but that is a toolkit that can kind of go after these types of things. So yeah.
So before we go into questions, a little bit more about protocols in industrial complexes. There's a lot of different protocols. We only went over like the 6 that are like open standards, but a lot of cases you just have like these vendor specific protocols that they use, and that's kind of what we went over, kind of just open standard kind of ones. There's a lot more out there, but these are the main kind of ones that we wanted to go over and are just kind of we've seen a lot of. through doing simulations and looking through malware reports and stuff like that. Yeah, this was like the end of the foundations part, because we kind of wanted to cover, just the basics of like components, protocols, and just what even OT is. Now we're going to be going a lot more into like malware deep dives. So like next week we're going to go into Frosty Goop, which we kind of mentioned a little bit during this meeting, but that was an ICS specific malware, because to be an ICS specific malware, you have to directly interact with industrial control systems, because a lot of like malware that's used in ICS environments can't be considered ICS specific malware because it just takes control of the GUI of of these operator stations and are able to just like do things from there. But yeah, so we also plan on doing like the critical infrastructure sector specific meetings where we talk about electric, water, all that kind of different stuff. But yeah.
Okay, thank you guys.
Yeah.
That is all we have for you today.